So now I want to get into the meanings of the operations because this is going to help us understand this order. We just talked about division as the how many groups, right? This idea of partitioning. Luly's method, partitioning in equal groups, gave us uh, the question of how many then is in each group. I knew I had 12 groups and I wanted to know, well, how many was in each group? Or this notion of Samuel's method of, well, of repeated subtraction, right? I didn't know how many groups I was going to make, but I knew each group was made up of that divisor, right? We did our divisor in the one example was 14. So we want to take out these groups of 14, whether it was 10 groups of 14 at a time or more, or even one group of 14 at a time, right? So this is how we're going to help us to understand the order in which we do them. And the next couple of slides are going to show an example of each of the operations with its meaning and a representation of each of the operations. Individually, first we'll go through addition, subtraction, multiplication, then division, and then we're going to put them together so we can start talking about the order and where this order comes from, so we can do it without using the acronym PEMDAS, because again, as we saw in class, the acronym PEMDAS is limiting, or maybe we heard in class and we don't quite understand it yet, and that's again completely okay. That's where we're gonna that's the point of this video. So let's first start with addition. And so it's fall. Pumpkins are some of my favorite things in the world. I don't know why. I just think they're adorable. I love them. I love pumpkin picking. I love going to pumpkin patches. But sorry, that's not for here or there. So we can just see addition as this idea of even counting, right? I want to see how many pumpkins I have. 1, 2, 3, 4, 5, 6, 7, right? I can count up, right? This is that notion of counting up. But maybe you see 3 orange pumpkins, 2 white, and 2 that light greenish. And so now we see this idea of addition, right? 3 plus 2 plus 2 is 7, or 3 plus 2 is 5, 2 more. Again, we can count up. And so when we represent addition, it looks like they're all there, right? The total, the sum. We're just looking at quantities being combined or put together. There's nothing else to do. So if you have 2 pictures next to each other, then that is showing addition. You don't need the plus sign in between, right? Because when you look at the picture itself, right, your mind is automatically thinking, oh, how many total is that, right? So this is where for addition we saw this idea of counting up or counting forward or combining, and I can even add, right, or put together, right? We're combining or we're putting together, putting sets, groups, quantities, ideas. Awesome. And I also want to show the number line as a way to represent addition, right? This idea of counting up. And I can count up I can start anywhere. Where do we want to start? 11, boom, 11. And then we can move forward, right? How many spaces? 1, 2, 3, 4. 11 plus 4 is my 15. I also want to connect to the idea that we did in week 3 of adding negatives. What happened with our 2 color counters and we added negatives? And unfortunately, the Explore Learning website isn't working right now. So you can go back to that video and watch how we can show that adding, right? But think about it, when we have positives and negatives, the meaning of adding is just to put them together or combine them. And that's why when you have some positives and some negatives, you get that sum to 0. I know you want to say they cancel out, but I'm going to encourage you not to. But you can think about that, right? Some are positives, some are negatives. And when you have the same number of positives and the same number of negatives, they sum to 0. And that's how sometimes your answer is more positive, right? If you have more positives than negatives. Sometimes your answer is negative if you have more negatives than positives. But again, with the number line representation, right, you can start anywhere and add any amount. So this is adding, is putting together, combining, or counting forward, counting up. So now let's check out subtraction, right? Here's a list of all the ways we can think about it. Counting down, counting back. So again, we can use the number line to show that. Removing or taking away. The distance or difference between numbers. Again, we can see that on the number line. Comparison. And when we get into positives and negatives, right, we can understand it as add the opposite. So I'm going to see, look at this set of eggs. We can see, I'll choose, I'll keep blue, right? We have, and oh, look it, we immediately might see an array now that we're used to that, right? 4 by 6. But you can see that there's also these 3 missing. So you can see this as, right, 24 minus 3, right? 3 are missing. And so, or this idea of take away, right? We could literally have taken them out of this egg carton. We could have counted everything that's there. We could have counted all of the spaces, or maybe we knew that this was 24 and then we wanted to just count back, right? 24, count backwards to 23, count backwards to 22, count backwards to 21, right? Count backwards 3 times. Right? And so back to the number line, look at, again, we can now, we want to show, show this idea of 24, count backwards, take away 3, or we can also see the number line here, right? 24 plus a negative 3. And this is where every subtraction problem is also an addition problem, right? It's add the opposite or add a negative, right? 24 minus 3 is the same as 24 plus a positive 3. And this relationship between addition and subtraction, or addition and negative numbers, or subtraction and negative numbers, right? Every subtraction is just adding the negative, is why we can then write every single subtraction problem as an addition problem, and then we can use the commutative property. So commutative property means any order works. You can go left to right, you can go right to left, you can switch the order, and it will always, always, always work. So if you keep the sign with the number, so if it's a -3, well, if you keep that as -3, you can put that anywhere in the expression as long as the sign, right, the negative, the minus, stays with that number. So here we go, right? 24 minus 3 is the same as 24 plus that -3 that we saw on the number line, right? They mean the same thing. That's the definition, the meaning of the equal sign. All right. Here is another way we can think about subtraction. Well, we can actually see more than one operation here, and I hope you're starting to see that. Right? First thing about this, maybe as addition, right? Again, I'm going to just look at the left set of pumpkins, and maybe I'm just going to start counting, right? Addition can be counting up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 pumpkins. Maybe I'm going to write that in black. Let me erase that. Right on the left. And maybe, one question could be, well, how many are there in total? So let's count the right side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Nice. Now we can add, right? A reason or a rationale and explanation, the definition, right? The meanings of addition, combine them, put them together. We want to know how many there are. And that's perfectly valid. But also now, what if I want to know is how many more, right? Now we have a ration, right? Now we want to compare. We want to compare these two sets, and that gives us this idea of 18 minus 16, right? Or the left side, right, has 2 more pumpkins. So this idea of subtraction as not only counting backwards or adding a negative, but it can also be this comparison, right? How many more does this one have? Or how many fewer does the other one have? And so let's bring it back to the number line. Here's our 18, and we wanted to find out how far away 16 was, right? We can think about it that way. And there's 2. The difference or distance between those is 2. And we can see that, either positive or negative, right? The distance or difference between 16 and 18 is 2. If we thought about it as take away, right? We continued with this idea of subtraction as take away. Now we can see 18 minus 16. Where do I land? Here at 2. So this is where the different interpretations also sometimes, have these different representations, right? The distance or difference between 16 and 18 is 2. But if we thought about it as 18 minus 16, right? 18 take away 16, and then that would mean we'd have 2 left over. So both are completely valid ways of understanding or thinking about subtraction. But in those different ways of interpreting it, we have different representations to show those 2 different meanings. Additionally, the context that you're in, right, when we're comparing our 2 sets of pumpkins, in no way are we taking away those 16, right? We still have one group of 18 and the other group of 16, and we're looking for that difference or the distance, right? We're comparing those 2 groups. So that's where we would want this piece, right? This representation of the distance or difference between these 2 numbers versus the idea of 18 minus 16, right? Take away 16 to go all the way down to 2. And now I know, right? What we just did addition and subtraction, and now we're moving into multiplication. And I know you were dying when I was counting these pumpkins by 1, right? Because we want to be more efficient. Look we could line up these pumpkins in almost an array, right? We can see 4, 4, and I know, sorry, 4 and 4. These 4 equal groups of 4. And this is how we develop the meanings of multiplication, right? We can go from skip counting to repeated addition, and then get into arrays and area. And so here are some examples of how we can show that. I have these packs of Matchbox cars. In each pack, there are 5, right? 5 cars in each pack. There are now 4 packs in each row, and then there are 2 rows, right? So I get this 5 times 4 times 2. And you could definitely see that way. But what if you saw it as, sorry, that 5 is ugly, bothering me. Well, I didn't see 5 packs in each. I first saw 2 rows. And then I saw 4 packs in each row. And then I saw 5 cars in each pack. So now I have 2 times 4 times 5. Again, 5 times 4 times 2 is the same as 2 times 4 times 5, right? This is the commutative property. And either way you see that is completely valid. And so this is why that multiplication can now happen in any order. And so I just have this picture of the crayon box, right? Think about, so that's one way to think about multiplication, right? Or maybe you see it as this array, right? You see 10 cars here and 10 rows, and how many columns? 4. 10 times 4. So I have the pack of crayons here to show, like, we can also think of multiplication as equal groups. If you have 12 packs of crayons and there's 8 crayons in each pack, right? How many total crayons do you have? So this idea of equal groups, arrays, the commutative property, right? All of this is how we can show multiplication, right? And I'll write our equal groups here for our pack of crayons. So we can have this as an array, or I mean, you could see the equal groups too in these packs, but another example. Again, one of my goals is for you to now see this math is everywhere. When you have packs of things, it's multiplication, right? And whether or if it comes in arrays, right? Multiplication, right? It's a way for us to be more efficient in our counting. All right, so let's bring it back to the number line. And we had, this distance or difference between 18 and 16 is 2, but I also want us to see the multiplication on a number line and skip and connect it to skip counting, right? We can go 2 between 0, oh, don't go that way, 0 to 2, another set of 2, right? 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, right? This is our skip counting. And now we can also see this as 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 9 groups of 2, or 2 9 times. And maybe, again, you want to compare, connect again to the commutative property. Well, I can have 9 groups of 2, or, oops, 2 groups of 9, right? And I'll end at the same spot. I don't know why. I need to start at, give us some space so we can see. Oh, I guess, yeah, clear. All right, sorry about that. That cleared everything. But play with this. See how you can see the skip counting. Maybe you don't like 2s, or 2s are too easy. Let's do 4s, right? We're so used to counting by 2s. 4, 8, 12, 16, 20, right? And how many 4s did we do? 1, 2, 3, 4, 5, right? And this is how we connect counting to skip counting to equal groups, all right, and get that multiplication. So the number line and or the real objects or the chips, right, the counters, can all be ways we can represent these ideas. All right, so last but not least is division. And this was part of for my one class, my one Monday, Wednesday, Friday class. I know everyone's going to be hearing this video, but I thought it was a really valid point. This was part of our checkout today. It's Friday, right? Here we see the division with this exact picture. This is the same one that I've used in all the classes, but I was a little confused because it doesn't represent the whole array, just part of it, right? That is exactly true. When we talk about division, we split it into these equal groups. And this is where the representations, the static ones like this as a drawing, is tough. But when we're thinking about division, we want to know now how, in this case, if we divide it into 2 groups, right, in each group. So we only want to look at one of these groups, right? We only want to look at, see how many is in one group, not in both groups, right? Even though both groups are still technically there in the picture, when we do this division, right, divided by 2, when we split this picture into 2 equal groups, our question was, well, we want to look at only one group. So I wanted to make sure that was clear for everybody to see. But now, I'm bringing us back to the Matchbox cars. Check this out. Again, a beautiful array. I know now you're seeing arrays everywhere and you love them, and you're immediately thinking of multiplication, but we're thinking about division, right? Pretend this is not a beautiful array, but a pile, right? A messy pile on the floor of all of these cars, right? They were dumped out of a bucket, dumped out of all these packs. But maybe I want to see them in these packs, right? So I have 8 packs. So the question, I know you want to ask it, right? How many cars fit in each pack? Right? Is one way you can think about this, right? This is our 40 cars and 8 packs. Or I don't know how many packs I have, but I know, right? I've been to sorry, I've been down the toy aisle at Target way too many times recently, right? I know that 5 cars come in a pack, right? I know how many is in one pack. So now what's my question, right? How many groups or how many packs, right? So then again, I know I have 40 cars and 5 fit in a pack. And so my question is, right, how many packs? How many packs can I fill? And this is where I want you to see this division and how to represent division and how to understand division in these two different ways, right? The pictures look exactly the same, but it's the questions that we ask in the context. So it's more than just the picture. It's our explanation of the picture and how we're seeing the numbers in the picture, right? Because this case would be 40 divided by 8, but this case would be 40 divided by 5, right? For the exact same pictures. So again, that's why the words along with the pictures, along with the numbers, that's what matters when they're all together, not any one individually.